Welcome to our video on the physics of elementary particles. Here we will discuss most important symmetries for the strong electromagnetic and weak interactions. We consider three symmetries under which interaction processes can proceed in the same way: parity operation, charge conjugation, and time reversal. As a first example, we use a strong interaction between a proton and a pion that exchange an up quark and a down quark. The strong interaction, mediated by a gluon, turns the proton into a neutron and the negatively charged pion into a neutral pion pi0. We consider here scattering processes where the energies and momenta of the incoming particles are large compared to their rest masses. On the right, we move to the center of mass frame of the scattering. The incoming particles are a proton from the left and a pion from the right. Single arrows show the particle momenta. Double arrows show their spins. Protons and neutrons have spin 1/2, while pions have spin 0. The parity operation is a point reflection. Left is the original scattering graph, right is after parity operation. Now the proton comes from the right and the pion from the left. Note that parity flips the momentum but not the spin. For strong and electromagnetic interactions, this mirrored process also occurs. The weak interaction is the exception, which we will discuss separately. Next is charge conjugation. The proton from the left becomes an antiproton. From the right, a positively charged pion comes in. The outgoing particles are an antineutron and a neutral pion pi0. Swapping particles with antiparticles is allowed in the strong and electromagnetic interactions. Finally, time reversal. The process runs backward. Incoming and outgoing particles are exchanged. A neutron and a neutral pion pi0 enter, and a proton and a negatively charged pion exit. This process exists in all three interactions. Now let us consider an example of a charged weak interaction process, where a positron and a d-quark exchange a W boson. With this interaction, the positron becomes an anti-electron neutrino, and the d-quark a u-quark. Sum up the electric charges before and after the interaction. On the left, the positron has elementary charge 1. Subtract the 1/3 negatively charged d-quark to get plus 2/3. After the interaction on the right, we have the neutrino with 0 charge and the u-quark consistently with plus 2/3 elementary charge. Electric charge is conserved, everything looks okay. In our example, the energies and momenta of the incoming particles are large compared to their rest masses. Again, we move to the center of mass frame of the scattering. The incoming particles are a positron from the left and a d-quark from the right. Single arrows show the particle momenta. Double arrows show their spins. We have a charged weak interaction process with W exchange. Thus, fast matter particles such as the d-quark on the right are left-handed. That is, the spin orientation against the momentum direction. The positron on the left is an antiparticle and is to be right-handed. That is, the spin is oriented along the positron momentum. Now we perform the parity operation. Upper left is the original scattering. Upper right is the parity-operated scattering. The momenta are flipped, but not the spins. Look at the spin and momenta. A matter particle such as the d-quark would be right-handed and the antimatter positron left-handed. This is not observed in charged weak interactions with W exchange. Therefore, we cannot perform a parity operation and receive a valid scattering process. We state that parity is violated in weak interactions. Now let us check the charge-conjugated process. In the original upper left scattering, we exchange particles and antiparticles to obtain the lower left scattering. Also here, the left matter particle electron would be right-handed, that is, spin along the momentum, and the right anti-d-quark would be left-handed with the spin against the momentum direction. Again, such scattering processes are not observed. Thus, in charged weak interaction with W exchange, the charge-conjugated process does not occur. In time reversal on the lower right, the scattering process runs backward. The incoming particles are the u-quark and the anti-electron neutrino. Outgoing are the d-quark and the positron. Check the spin orientations in comparison to the momenta. Everything looks okay. Matter particles are left-handed and antimatter is right-handed. The symmetry of time reversal is fulfilled in weak interactions. Now we combine the charge conjugation and parity operations in our charged weak interaction process. On the upper left, we see again the original scattering process. Upper right shows the forbidden charge conjugation with particles and antiparticles exchanged. Operate on the forbidden charge conjugated process with the parity operation. Parity changes the momenta but not the spins. The incoming anti-d-quark enters from the left and is correctly right-handed, and the incoming electron from the right is correctly left-handed. The miracle happens. The combined symmetry operations of charge conjugation and parity results in a valid scattering process for the charged weak interactions with W exchange. Look at the table of symmetry operations in all three interactions: strong, electromagnetic, and weak. Strong and electromagnetic interactions are symmetric under parity and charge conjugation, while weak interactions are not. All three interactions follow the time reversal symmetry, that is, processes can run backward in time. Combining symmetry operations helps. For most weak processes, the combination CP is effectively respected in the sense that the CP transformed process also occurs. Still, in a tiny fraction of scattering processes of about 10 to the -3 violations of the combined charge conjugation and parity symmetry operation have been observed. The combined symmetry of all three operations CPT is respected for all three interactions. We discussed symmetry operations and saw that strong and electromagnetic interactions respect all of them. The weak interaction is not symmetric under parity or charge conjugation. Combining the symmetry operations charge conjugation, parity, and time reversal works in all three interactions. Enjoy studying particle physics.